Okay, so this is video 2 of 3 on trigonometry for Math 1560 Calculus 1 at U of L. And in this video we're going to introduce the sine and cosine functions. Now I'm hoping that you're all familiar with these functions, but it's always a good idea to review these. Trigonometry tends to give students a fair amount of grief at some point or another in calculus, so it's a good idea to take a quick look at these guys. Now, how do we define sine and cos? Now, there's two ways to define the sine and the cosine functions. There's one definition of sine and cos that has to do with right-angled triangles that you've probably encountered, right? You draw a triangle. This is a right angle. This is theta, and you've got the opposite side, the adjacent side, and the hypotenuse, and you've probably seen this sort of definition. You know, sine theta is equal to opposite over adjacent, and cos theta is equal to, sorry, opposite over hypotenuse. Let's get these right. Cos theta is the adjacent side over the hypotenuse. You probably remember seeing these sorts of definitions of doing triangle trig, but we want to do circular trig for calculus because we want to define sine and cosine as functions of a real variable that we can do calculus with. We saw in the last video that using radians allows us to identify angles with real numbers, so we can now think of these things as functions of a real variable. But how are these functions defined? How do they behave? Well, the first thing we do is realize that if we take this triangle and we rescale everything so that the hypotenuse has length 1, we can situate everything on the unit circle, right? The unit circle has the equation x squared plus y squared equals 1, and we simply define sine and cos as coordinates on the unit circle, right? So the x-coordinate of, so we've got a point on the unit circle here, the x-coordinate down here, right? This distance is cos theta. The length of the adjacent side, remember we're rescaling so that h equals 1, length of the hypotenuse is the radius of the circle, and this length here, the length of the opposite side is sine theta. But now we can think of these as kind of the width and the base and the height of the triangle, if you like, or just x and y coordinates on the circle, right? So cos theta is basically the x-coordinate, sine theta is the y-coordinate for any point on the unit circle, and since we know that x squared plus y squared equals 1 for points on the unit circle, we get the one trig identity that most people are able to remember, which is that cos squared plus sine squared equals 1. Most people tend to remember that identity, and this is how you come up with it. It's simply a fact of the definition of the sine and the cosine functions. Okay. And by the way, I'm calling them functions. How do we know they're functions, right? Well, certainly once I choose an angle, that angle uniquely defines the point P, right? There are not going to be two different points that correspond to the same angle. There certainly are many angles that correspond to the same point, but once I know the angle, there's only one point that's going to work. And once I know the point, well, there's certainly only one x-coordinate and one y-coordinate. So we are definitely getting functions out here, okay? And because we can identify angles with real numbers, these are now functions of a real variable. Okay, so what can we do with them? Well, one thing we can do is work out some values, right? We don't know anything about these things yet. Do I know any values at all? Well, probably at some point you guys learned your special angles on the unit circle, right? So pi over 4 in degrees, this is 45 degrees, right? Pi over 6, 30 degrees. And the other one of interest is pi over 3, which is 60 degrees. Okay, those are kind of the three common angles. Well, I mean, there's a couple of easy ones, right? 0 degrees. Well, we know that point is 1, 0, so we know right away that cos of 0 is 1. We know that sine of 0 must be 0, because those are the coordinates for that point when the angle is 0. And up here at the point 0, 1, we see that cosine of, so this is a right angle, 90 degrees in radians, that's pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so I'm interested in these angles, so the 30-degree angle, the 45-degree angle, and the 60-degree angle. We want to work out the sine and cosine values for them. For other angles, it turns out there aren't nice numbers that you can give. So the reason we give the values for those three angles, that those are really the only other ones where we can give nice values, at least in that first quadrant for angles between 0 and pi over 2. Something that we could talk about, we're not going to put it on this video. This is something you can come see me about if you kind of forget how this goes or you need a little help with it. There's the issue of related angles and coterminal angles. All these, so we know that you can always add a full revolution to pi. So a full revolution equals 2 pi radians, right? So I could say that at this point here, theta is equal to 0, but I could also go with 2 pi or 4 pi or minus 6 pi, right? Any multiple of 2 pi gets me to that same point on the unit circle. Similarly, pi over 2, there's lots of ways I could write that. But then also you want to deal with angles in the other quadrants, right? If you're over here, when theta is equal to pi, well, that's the point minus 1, 0, so we get that cosine of pi should be minus 1, sine of pi should be 0, and so on. But what if I want to do something like, 2 pi over 3, right? We're going to show on the next slide how to get the value for pi over 3. So once I have pi over 6, pi over 4, pi over 3, how do I get the corresponding angles in the other quadrant? Well, I use the fact that the circle is a very, very symmetric object, right? So if this is, if pi over 3 is here, 2 pi over 3 is here, they're mirror images of each other on either side of the y-axis. And if you reflect something across the y-axis, you just change the sign of the x-coordinate, right? And so once you know these values, the other values in the other quadrants are the same up to possibly a sine factor. And the way you figure out that sine factor is simply by knowing where you are. If you're in the quadrant over here, well, you know that x is negative, y is positive, so the cosine should be negative, sine should be positive, and so on. But let's first see how do we actually come up with the values in the first quadrant. Well, how do I do the 45-degree angle? Pi over 4. Well, what does symmetry tell me in the case of pi over 4? We know that it's half of a right angle, right? Which means we're kind of looking at half of a square. These two sides have to be the same. So for a 45-degree angle, right, we're cutting this right angle in half, and it's not hard to argue that x has to equal y in this case. And so since we know that on the unit circle we get x squared plus y squared is equal to 1, well, y equals x, so x squared plus x squared equals 1. 2 times x squared is 1. So x squared is 1/2, and that tells me that x has to be plus or minus 1 over the square root of 2, which some of you might have been told you have to write as root 2 over 2, rationalizing the denominator. Nobody cares if you rationalize the denominator, but feel free to do it if it makes you feel better. And so that is also, of course, the y value. Okay, so x and y are both equal to 1 over root 2 when theta is equal to pi over 4, and so that means that cos of pi over 4 is 1 over root 2. Sine of pi over 4 is 1 over root 2. The other diagram here tells you how to get the values for both pi over 6 and pi over 3. So what I've done here is I've taken this angle which has pi over 6 in one corner, pi over 3 in the other corner, and of course the right angle in the remaining corner. And if you take this triangle and double it, it's not hard to see that you're dealing with an equilateral triangle, because then this angle is pi over 3, this angle is pi over 3, and since the angles in a triangle have to add up to pi, that angle is pi over 3 as well, right? And of course we can see that if you're just doubling pi over 6, yes, of course you get pi over 3. That means that you're dealing with an equilateral triangle, so all three sides have to have length 1, And then we can see that in our original triangle, well, the original triangle on that far right-hand side, this side is simply half the whole thing. So this length must be 1/2. Okay? So that tells me that sine of pi over 6 is 1/2. And then using the identity, since we know that cos squared pi over 6 plus sine squared pi over 6, we know that that should be equal to 1. Well, I'll leave it as an exercise for you to work out that means that cos of pi over 6 must be root 3 over 2. I should mention I didn't explain away the sign here, right? We want to keep the plus sign for these values simply because if we're setting up, if we're working with pi over 4, we're in the first quadrant where x and y are both positive, so obviously we want the positive root. Okay, and then you can kind of turn the exact same argument around, and you can come over and think about this triangle starting up here in the upper corner, where the angle is pi over 3, and you can realize that, well, you kind of flip the picture around, roles are reversed, and if you kind of go through the exact same argument, you find that sine of pi over 3, well, sine and cos kind of trade spots. So sine of pi over 3 becomes root 3 over 2. Cos of pi over 3 becomes 1/2. So that's how you work out these values for these special angles. There are various tricks for trying to actually remember them. Feel free to ask me about those if you want. With a bit of, some people will complain about having to remember these, but it doesn't take too much work, and mostly simply by using these things repeatedly throughout the semester, you'll probably find that you remember these without trying by the end of the semester. If you don't pull out your calculator every single time you need to look one of these up, you'll find that, yeah, as you work with them, you get used to these values. They'll sink in by the end of the term. Now, we want to move from thinking of sine and cosine as coordinates on the unit circle to thinking about them as functions of a real variable, as these two functions with these two graphs. So the curve in red is the graph of the cosine function. The curve in blue is the graph of the sine function. How do you come up with these graphs? Well, let me show you one way to see where this comes from. Here I've plotted a couple of things. On the left, I've plotted a unit circle, and I've got a point on that unit circle and a corresponding angle. Okay, so t here is the angle in radians measured between the positive x-axis and the line that you see. Over here on the right, I've got 2 points, P and Q. So point P is the x-coordinate of point P is given by t. The y-coordinate is given by, well, cosine in the sense of the x-coordinate of this point. So you'll see that, let me move this point a little bit. Okay. There it is. And you can probably see here on the left that the number, the 0.95 that you see here for the x-coordinate of this point, that becomes the y-coordinate for the point P. You can see that here. And the y-coordinate, 0.32 for this point on the unit circle, that becomes the y-coordinate for this point Q, sitting right here. Okay, and so what you can do is you can move this point around, and you can watch P and Q and see what they do as I move the point around the circle. Okay, you can watch those move around. They move around. Okay. All right. Can we learn anything else about these guys? Well, let me turn on, so there's this trace option I have here. Turn on the trace. This is going to allow me to track the motion of those 2 points as I move this guy around the unit circle. So what happens as I move it around the unit circle? Okay, there they go. So we'll watch them go. By the way, on the right-hand side, things aren't perfectly to scale because I wanted to make sure I could fit a full revolution in. So you'll notice that the x-axis is squished relative to the y-axis. But you see these curves showing up. These curves are exactly the curves that you see when you plot the sine and the cosine functions. There they are again. Okay. And so that's how you come up with these graphs for the sine and the cosine functions, or that's one way of thinking about it. And then if you want to move beyond the unit circle and you do want to come back to right-angled trig, because there are going to be some applied problems where you have to come up with right-angled trig, well, then you're back to, you know, this situation where you're dealing with a, let's see, a right-angled triangle. This side is now some length r. This is my angle theta. This is my x. This is my y. So in general, cos theta is going to look like x over r. Sine theta is going to look like y over r. So you might see a few situations where you've got to deal with that, but for the most part, we are thinking of these as functions of a real variable, and we are thinking of them as functions that are defined using coordinates on the unit circle. Okay, one more video on trig and we'll be done with our review.